You've learned this interesting fact that every time you run a statistical test, when the null hypothesis is true, there's a risk of committing a type 1 error, of saying, hey, something's significant when there's actually nothing going on in the real world. This can be a little disconcerting for some students. Like, so a lot of the stuff I'm reading is just bull plop. Yeah. Well, it's not really wrong because these are the rules of when we're playing the game. Once you set an alpha level, you're saying, hey, I might make a type 1 error. If you don't want to make a type 1 error, what would you do? Well, you would change your alpha level. If you're not comfortable with going around saying there's a 5% chance, blah, 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 well, tighten it up. Tighten your alpha to 1. Sorry, 0.01, 1%, or even smaller than that, right? When they were looking for the Higgs boson, the so-called God particle, the researchers did not want to make a type 1 error. So they cranked their alpha level down. I don't remember the exact number. You can look this up. It's true. They cranked their alpha level down to something like 0.00000, maybe 12 O's or 15 O's, 1, to really reduce the risk of a type 1 error. What's the flip side of that? Well, it kind of turns up your risk for a type 2 error. So we have to think about, we might want to change that alpha in certain situations. And this is the idea of maybe we adjust for multiple comparisons. Now, a lot of people have thought about this issue of multiple comparisons. If you don't want to make a type 1 error, but you know you have to run a bunch of different tests, what should you do? And I think it's pretty obvious that you just need a tighter criterion or a tighter standard, or I'm going to need more evidence. Bonferroni was a guy who said, this is a very simple thing to do. It is take whatever your alpha is that you want and just divide it by the number of tests that you're going to run. So instead of 0.05, if you're running 10 tests, use 0.005. Now, it's worth stating again or reinforcing, if you run multiple tests, like we're going to put this in the context of ANOVA, where we say, hey, the null hypothesis, we reject it. Not all of them are true, right? Not all of them are equal. Where is the specific difference? I need to run a bunch of t-tests. Maybe I need to run 10, so I'll change my alpha to this. But this is also true for like any time you're running a bunch of statistical tests. If you have, say, a regression model, a multiple regression model, and you have a ton of predictors, some predictors that are actually, they do nothing in the real world will show up as significant. If you test things that aren't significant, 5% of them will show up. You can even think about it like over your life. If you test dumb question after dumb question after dumb question after, if somebody will fund you long enough to let you do a bunch of statistical tests, eventually you will find something statistically significant. But if we want to be tighter, if we don't want to do that, we crank down our alpha, so we're less likely to make that type 1 error. But then, of course, the flip side is we're more likely to make a type 2 error. And if you go back to our analogy of the justice system, you'll see that this is true. If you really, really don't want to convict any innocent people at all, you get a really high standard of evidence, and some guilty people you're going to let go free because that standard is going to be really hard to meet. You get to pick the alpha level when you balance out how much type 1 and type 2 error do I want. So Bonferroni's approach would say, let's say you run a bunch of t-tests. So here I ran all of these t-tests to see if there's a difference between how many hours per week you work and what your education level is. And we saw that some of these were statistically significant. But some of them, the signal wasn't really that strong. Look at this, bachelor versus high school. An hour and a half extra per week, and the p-value equals 0.04. It's funny because when the p-value equals 0.06, you see people use this really stupid phrase, oh, it's borderline statistically significant. But when the p-value equals 0.04, you would never hear anyone say, oh, they would never say it's borderline here. They would just say, it's significant. I found a significant result. But think about this for a second. I've run a ton of tests, a lot of p-values. Is it possible that this one is just a type 1 error? That there really is no difference between people who have high school degrees and people who have bachelor degrees? So if we had been rolling with alpha equals 0.05, we would have said this is significant. But if we're doing something like a Bonferroni correction and we count up how many of these tests there are, we take that 0.05 and we divide by the number of tests. It's a stricter standard of evidence. And 0.04 now would be no longer statistically significant because it's not going to reach that standard. See? Now, Stata has this cool thing where what Stata will do is it will take that Bonferroni correction and it will change all of your p-values and put them on a scale so you can actually use your 0.05 since we're used to it. So I'm going to run this same set of t-tests, same data, same research questions, same people, same hours, same education, everything, but all I'm going to do is change my alpha. Watch what happens to this 0.04, this significant result. To run this in Stata, I'm going to do a one-way ANOVA. So we have our outcome, mean number of hours, and then we have our group variable. And then I'm going to do this post hoc adjustment. So in Stata, you know that I put this comma in here, and then that lets me specify options. And the option that I want is this Bonferroni thing. And then I see this tabulate. That's a verb. That means put all this in the table, right? Put all this in the table. Oh, sorry. And what you see is we were comparing, I can't remember. I have to go back. Sorry. Bachelor versus high school. Bachelor versus high school. And what was that difference we saw? We said it wasn't that much, like 1.5, 1.5, 1.5. And what's the p-value? It's not significant. People don't like this. Students don't like this. Wait, you're telling me that you're telling me that there's a difference, but if I just tell Stata to do things a different way, now there's not a difference? Like, well, what is it significant or not? Is it real or not? What's the right answer? There's no right answer. There's no right answer. It tends to be that you will eventually become a person who adjusts for multiple comparisons. And Bonferroni is just one way to do it, but there's lots of other ways we'll see in a minute. Or you'll become the type of person who doesn't adjust for multiple comparisons. And you'll just say, hey, look, I got a P of 0.04, but it could be a type 1 error. That's up to you to decide. And you're going to see that a lot of things in the practice of statistics that are not black and white. There's some art and creativity and some common sense that has to get involved as well. If you want, take that example from tabulating the data with this, mean sharing the same scooper script. Make the same table based on the original data, the unadjusted. It's really funny. We didn't say unadjusted at first, did we? Oh, no, we did actually. We did. We said unadjusted. So there's almost like this implied thing that you should adjust. It's up to you to decide. But compare it to what happens when you have the Bonferroni correction. You will have fewer things that show up as statistically significant. Why? Because you have a tighter standard of evidence. Good. Lower risk of type 1 error. But not good. Higher risk of type 2 error. Maybe you're letting the guilty man go free. You're failing to detect a difference where one exists. What do you want more of? Type 1 or type 2 error? I am filming this on June 2nd of 2020, and we are in what we think is the second wave of what we are calling today COVID-19, what we are calling today a pandemic. And one of the biggest things we're debating, we talked about it before we hit record today, was what is going on with antibody testing. Now, I hope when you are watching this video that you say, man, those guys didn't know what they were doing. We solved that problem real quick. Because right now we are running tests that are not perfect. Some of the tests give back false results. They say, hey, you have no antibodies when you actually do have antibodies. Because the tests aren't really powerful enough. You can almost think of an antibody test like a magnet, and the magnet goes into your blood and it tries to pull out if you have these antibodies or not. Well, if your magnet sucks, it's not going to pull out the antibodies, right? So those tests give a lot of false negatives because it didn't pick up the signal. Some of the tests that are out there now give a lot of false positives. They go off when there's really nothing there. They're picking up signals from other coronaviruses, not the specific one that, as of this writing, we're all freaked out about because there's a 10% case fatality rate. And I think we've had like 110,000 deaths in the United States. So we're running tests that might be a false positive or they might be a false negative. That false positive, this is a good analogy. That false positive or that type 1 error, it's like a smoke alarm that goes off way too much. Do you have one of those smoke alarms like you take a shower that's too hot and it steams and then your smoke alarm goes off? That smoke alarm is way too sensitive, but it's okay. You just press the button and it goes off. It might take a little bit to calm your dog down. That's fine. But would you rather have a really sensitive smoke alarm or one that's not that sensitive? Probably a really sensitive one. So thinking about designing a test, how sensitive do I want it? Or do I want it to be really specific and only pull out the right antibodies? Right now, we're running blind. And in Epi, you learn a lot about these screening tests. So let's think a little bit. Type 1 and type 2 error. I have to find that balance between false positives and false negatives. I get to pick as the researcher. And lots of people have come up with different ways to sort of think about balancing that type 1 and that type 2 error. The first thing we did, and we didn't talk about in this context, was what Fisher said. Fisher said, hey, just run all possible t-tests. And you're kind of protected because the first thing you did is you looked overall. Overall, you look to see, are these all equal to each other? And that's one test. You ran that F test. And the probability of making type 1 error with that test is 5%. And he said, if that is significant, then go ahead and run the t-test and interpret them, smart. Now, there are a lot of other people who came up with stuff. And these are stricter and stricter and stricter. And depending on what you decide to do, what other training you get, who you are influenced by, what field you go into, you will see these different adjustments for multiple comparisons. Now, we are going to talk about the flip side of this, type 2 error.